Hi. Today what I'd like to do is discuss an application of Green's theorem to finding areas of regions enclosed by simple closed curves. So let's just remind ourselves what Green's theorem says. It says that the line integral around the closed curve C, p dx plus q dy, is equal to the double integral over the region D that's enclosed by the curve C of partial q partial x minus partial p partial y dA. Okay? So let's recall something that we learned about in when we started to study double integrals, and that was the following, was that if we had some area D enclosed in the xy plane, maybe it looks like this somehow, and this would be the area D, then we could find the double integral of some scalar function over the region D. And if you do that, what you're really doing is that this region D, if we were to trace up all of the points on the edge, up through points on the surface above, we end up with a copy of D somehow, or some kind of region up here on the plane. I'll call it D star. And D star is the section of this sheet, or this scalar function that I'll call f of xy that gives us z. And I'm saying D star, this region D star, is the region that would have a shadow in the xy plane of the region D. All right, so you can tell by the way I've drawn this that these heights at different points inside this region, if I looked up here and I found all the values of the heights, that they wouldn't all necessarily be the same. And you can tell that because this region is curved somewhat. Well, imagine instead we had this. We had a double integral again over some region in this plane, and we'll call it D. But the scalar function we're interested in was a very simple scalar function. It looked like a plane parallel to the xy axis, and its equation is f of xy is equal to 1. Well, that's kind of a special case, because if we think about tracing these points up to this surface here, and we draw the region D star, what the region D star looks like, my picture's not so good, but it's really a perfect copy of the region D below. It's a copy of this region up here, projected exactly 1 unit above the xy plane. And therefore, if we were to compute this double integral, it would be the double integral of 1 dy dx, or dA, over the region D. Well, what we're really doing is we're taking every point in the region D and we're assigning it a z value of 1. So in essence, every point in the region D gets multiplied by 1. Every little rectangular area down here gets multiplied by 1. And what you end up is adding up all these little areas, dx, dy, dx. Well, this turns out to end up equaling the area of D. Okay, so the double integral of 1 dy dx is the area of D. Well, if we go back to Green's theorem, and we specifically look at this side, then something very nice can happen. We can find the area of a region enclosed by a curve if the following is true. So if partial q partial x minus partial p partial y equals 1, then we would know that the double integral of this expression, partial q partial x minus partial p partial y dA, would give the area of D. Well, there you go. All right, so then what are the possibilities? Well, let's think about what P and Q might equal in such a way that this could happen. Well, think about this case. Suppose P of xy was equal to 0, while Q of xy was equal to x. Well, if that was true, then this expression in here would become basically 1 minus 0, which is just 1. So this is one way, one combination of P and Q that would give us the area. Okay? And you might say, well, why would I even want to do this? But well, if you think about it, what we can do is we can take a double integral with Green's theorem over here on the right, this double integral, and turn it into a single integral. So that's sort of the advantage here, and that's why sometimes it might be easier to calculate if we know that. What are some other ways we can do this? Well, how about this? If p of xy equals negative y, then q of xy equals 0. If you thought about that, then partial q partial x minus partial p partial y, well, that would be 0, because the partial derivative of 0 is 0, well, with respect to x, that is, minus, and then the partial derivative of p with respect to y is negative 1, but that's equal to 1 also. Right? And then one last special way to do things, we can do this, sort of a fancy way to think of it. We can do negative a half y for p of xy, and for q of xy, we can do 1/2 y. And sure enough, if you try that again, apply Green's theorem here, apply this, let's find the value of this expression. Q dx, I made a mistake there, hold on a second. This should have been negative a half x here, forgive me. Okay, that's better. So dq dx is 1/2 minus dp dy is negative 1/2. Sure enough, you get 1. So there we go. All right, so what I'm going to do is find the area of a pretty famous shape. We all know about the area of a circle. And that area is equal to pi r squared. Less people know about the area of an ellipse. Well, I'll give you a little hint, and then we'll see. You could, on your own, decide what you suspect, and then we'll see at the end if you were right. Well, you can think of an ellipse as a circle with sort of a larger radius in one direction, maybe we'll call that A, and then a small radius in another direction, maybe we'll call it B. So that's my hint to you, and then think about Ariel, I won't even say. I'll tell you there's a pi in it, and there's some other stuff over here. And the question is, what other stuff would go here that would be analogous to having the r squared for the circle? Okay, here, one more major hint. This is also a radius. Okay, so maybe you have a suspicion now. Let's do a little bit of work here. So that's our goal, is to find the area of the ellipse, whose equation is x squared over a squared plus y squared over b squared is equal to 1. And that's exactly the ellipse I described on the prior page. Half of the major axis is A, half of the minor axis is B. Okay, so what do we know? By Green's theorem, we've got a couple of ways to write this. We can say that the area enclosed of this thing would be the integral of x dy, or negative of the integral of y dx, or a half the integral of c x dy minus y dx. And you might say that's in the wrong order. Well, it really started out like this, negative y dx plus x dy. So I just reordered things. Okay, I'm going to use this last form. Okay, now the only labor, the part of this that requires a little labor is that, yeah, we want to evaluate this integral, 1/2 the integral of x dy minus y dx, but you can't do that until you've parameterized the ellipse. So you know something about parameterized equations. The parameterization for an ellipse looks like this. It's a cosine t for the x-coordinate. Oop, my mistake here, hold on. And then the y-coordinate, it's going to be b sine t. And we want t to go between 2 pi and 0. And that would give us the whole ellipse. All right, so if we sub things in here, actually, it turns out to be pretty nice. Wait, you see what happens. So here we go. We got a half the line integral from 0 to 2 pi. And x is just a cosine t. Oh, hold on a second there. A cosine t times dy, well, the derivative of this thing would be would be b cosine t. Okay, there we go. Minus y. Well, y is b sine t times dx would be negative a sine t. And this whole thing is being multiplied by dt. Well, watch what happens next now. Both of these terms, if you look at them, they have a common factor of a times b. So I'm going to factor that out, and that's actually a constant with respect to the variable t. So it can come all the way out in front. We get a half ab, and then we get the integral from 0 to 2 pi of cosine squared t plus sine squared t. All right, but that's not a hard integral to do at all. That's exactly 1, right? This thing's equal to 1. So the antiderivative of that is going to equal 1/2 AB times t evaluated from 0 to 2 pi. But that's not hard at all. Plug 2 pi in, minus 0, and you get 2 pi. So you end up getting 1/2 AB times 2 pi, or pi A times B. And I wonder if that's what you thought my hint was at the beginning of all this when I asked you to look at these two pictures. Okay? So it really is analogous. So that's a fun little thing that you can derive using Green's theorem. Thanks for watching.